describe the single transformation that takes y equals x cubed to y equals x cubed minus 8. Now, if I call this one f of x, the x cubed, then this would be f of x minus 8. And you've got to learn and understand the rules here. So this is actually a translation by minus 8. We're finding a value out. Like when we put, for example, 1 in, we'd get 1. And then we're minusing 8. So for my value of 1 here, I'd get 1, 1. But for my value of 1 here, I'd get 1 minus 7. So you can see we're just minusing 8 from the y value, and that's going to mean it's going down by 8, but what we say is that it's a translation. You can either say it's a translation by minus 8 units in the y direction, or just to make things a little bit easier, let's use vectors. Translation by 0, minus 8. Then the function f is defined by this f of x equals x cubed minus 8, and we're asked to find an expression for the inverse. So there's a nice way to do this, and I will talk a bit about what's going on, but we just say that y is equal to x cubed minus 8. Now this is taking me from an input to an output. So if I want the inverse, I want to go from the output to the input, so I need to make x the subject. X cubed will equal y plus 8, and therefore x will equal the cube root of y plus 8. And we could draw a little flow diagram. We can see that I'm going from x, and then I'm cubing it, and then I'm minusing 8, and I'm getting y. So I'm going the opposite way. I'm going to be adding 8. I'm going to be cube rooting, and that's going to get me back to x. But when we write an inverse function down, we always use x as the input. So now I just need to swap these two around. Sometimes people swap them around right at the beginning. I like to do it at the end. So the inverse function is going to be the cube root of x plus 8. That's part B. Finally, let's take a look at C. State how the graphs of y equals f of x and the inverse are related geometrically. Now, in fact, this is true for any pair of functions with the function and its inverse. So let's just say, for example, actually, I will pick a point on x cubed minus 8. So if I put in 1 into here, I would get minus 7 out, like I had before. So 1 minus 7 would be down here. Now what happens for the inverse is that the output now maps to the input. So we get minus 7, 1. It'd be up here. But that is going to be true for all our values. Instead of the input mapping onto the output, that same output is going to map onto the input. And basically we're going to get wherever xy is, it's going to become yx. And this always happens, and what you end up with is necessarily a reflection in y equals x. Because when you swap them around, that is precisely a reflection of y equals x. So words to this effect here. It's going to actually help us sketch the function. I think I'm going to go with it. So, right, I know I've got x cubed minus 7. So we know that x cubed looks a bit like this, but I've translated it by minus 8, so it's going to come down like that. And I'll just carry it on a little bit more. Now this can help me sketch the inverse actually. I know it's going to be a reflection of y equals x. Actually, that tells me that the inverse is also going to go through that point there. And then I know that 0 is going to map onto minus 8. If I swap that around, then minus 8 is going to map onto 0 for the inverse. So it's going to end up over here. And then this point here is 2, because 2 cubed minus 8 is 0. So my intercept up here is going to be 2, because 0 is then going to map onto 2. And I can start to see the shape. It's going to kind of go a bit like that. Okay, and if you tilt your head, you can see that's a pretty good reflection. There's the line of symmetry. It's the same distance to each point. So that is just a little bit away from the question how you can plot an inverse pretty effectively using the ideas of the mapping the points the other way and looking for the reflection.